The second derivative is -5. Second derivative tells us concavity. If it's positive, when it's positive, that means concave up. Negative means concave down. So when I see that the second derivative is a -5, that tells me my graph is concave down. So I knew it was either a maximum or a minimum, and my graph is curving downward, so what is it? A max. We have a local max at 2. Okay, part B tells me the first derivative is 0. So first derivative 0, that means it's either a max or a min. And the second derivative is 0. That means it's an inflection point, right? So my concavity is changing there. Okay, so it was a max or min, but my concavity is going to change from concave up to concave down, or vice versa. Does that tell me anything? No. I don't know which direction it was curving, so there is no conclusion here. I don't have enough information to know what that means. Questions on that one? I did have a question on problem 4 too, so I will talk about that one. So this one asked me to find absolute max and min. Anytime I want maxes and mins, what do we have to find? Derivative. We need our critical points. So we just need the first derivative here. Is 6x squared minus 6x minus 12. And I need to know when that is 0. What can I take out of all this? So then we could do box method. Multiply -2 and add to -1. -2 and +1. So my critical points, everything that makes that 0. The 6 never equals 0. What makes x minus 2 0?
2.
So what would make the x minus 2 0? 2. And the x plus 1? Thank you.
You're welcome.
Then -1. So I have 2 critical points. Alright, absolute maxes and mins mean it can happen at a critical point or the endpoints. The interval was -2 to 3. First, make sure, are both of your critical points in that interval? Yes. If one wasn't, we would throw it out. Then we are going to test all of those. The critical points and the endpoints. We plug these into the original and see what we get. So when we put in -2, -3. When we put in -1, 8. Put in a 2, -19. And put in a 3, what'd you guys get? -8. So the absolute max and absolute min are just the highest and lowest y values here. So I can see this would be my absolute max. And that would be my absolute min. Okay. that all right, everyone? Next page, 5 through 11. What do you want to talk about? Nine. 11. 10. I'm going to go ahead and do number 8 as well. I'd like to review both roles and mean value theorem if that's okay. So I'll do one of each. When you do these problems, you have to check the conditions. Number 8 is Rolle's theorem, and there are 3 conditions for Rolle's theorem. The first one is that it has to be continuous. Second one, it has to be differentiable. And the third condition for Rolle's is that the endpoints are equal. So if I'm looking at this, how do I know it's continuous and differentiable? Yeah. Alright, so if I gave you one of those problems, you do have to state that. If you're not showing that you know it has to be continuous and differentiable, you lose some points there. Then we need the endpoints to be equal. So we are looking at 1 and 3. If you plug a 1 in to your problem, we get -4. We put in a 3, we get -4. So these are equal. So Rolle's theorem applies. Okay, that's just telling me that I can do Rolle's theorem. What does Rolle's theorem tell us? What's the conclusion for this theorem? So in mean value theorem, the slope between the endpoints has to equal the derivative at some point. Rolle's theorem, it said that the derivative had to equal 0, but isn't that the same as the slope between the endpoints because they have the same y value? So it's really just a special case of the mean value theorem. So we need to find our derivative. And that would be a -12 plus 6x. Set that equal to 0. And we get +2. And so that's the number that we were looking for. It was in the interval 1 to 3. So this would be something that I strongly recommend studying before tomorrow, just making sure you know what Rolle's theorem says and mean value theorem says. You have to know their conditions and what the theorem tells us. So number 9 is mean value theorem. It only has 2 conditions. And it's the same as the first 2 conditions of Rolle's. It has to be continuous and differentiable. Again, this one is a polynomial, so it's continuous and differentiable everywhere. Things you have to watch for are like fractions. They wouldn't be continuous at the denominator value. If you have like a piecewise, it's not going to be differentiable at the break in between the pieces. But most of the ones we worked with were polynomials on these. Then it tells us that somewhere the derivative equals the slope between the endpoints. So we need the slope. When my 2 endpoints were -2 and +2, to get the y's, you have to plug those into the original. So if you put in -2, we get -8. We get 0. If you put in a +2, you get 8. So you get 4. So the slope between those, y2 minus y1 over x2 minus x1, you get 4 over 4, so my slope is 1. So what that tells me is my derivative has to equal 1. So our derivative is 3x squared minus 3, set that equal to 1. So 3x squared equals 4. plus and minus, you have 2 over radical 3, which would give you a 2 radical 3 over 3. You should check that those are in the interval, and both of those are. So we have 2 numbers that make it work. Is that one okay? Are you guys comfortable with what those 2 theorems tell you? That's probably the piece that you're least familiar with because it's been a long time and we haven't been using that in everything else that we've done. Question number 10, you have to draw a function. So more than one possible graph for this. It's continuous from 1 to 5. Okay, doesn't mean that it has to start and stop at those points, but it can. It just has to exist between them. We have an absolute min at 2. So the lowest point on my graph happens when x is 2. The absolute max at 3. So the highest point on my entire graph has to be when my x is 3. A local min at 4. So it's low, but not the lowest on the entire graph. Okay, so we just need a graph that meets these requirements. And my points are just slightly off, but you guys get the idea. Again, many possible graphs there. This is just one such graph. Is that one okay? Problem 11 has us looking at the graph. By the way, is this anybody's calculator in here? It was brought to me. I have no idea where it came from. Okay. I want all the absolute and local maximums and minimums here. So the absolute max has to be the highest point on the entire graph. Can those be endpoints? Absolute can, but local cannot. Okay, so we can see the highest point on the graph is right here. So you could either write an ordered pair, that would be 4 or 5, or you could say f of 4 equals 5. Either way. Absolute min, the lowest point on the entire graph, it can be an endpoint. If I look, the lowest point on my graph is right here, but what kind of circle is that? That's an open circle. So do I have an absolute min? No, there is none. Okay, local maxes and mins. We can have more than one of these. They can't be endpoints, but they just have to be higher than surrounding points. So local max, like this would have been a local max, but it's open, so it doesn't count. So I have a local max at my absolute max, 4 or 5, f of 4 equals 5. Do we have another one? We have one more. At 6, 4. F of 6 equals 4. Again, that's not an endpoint. It's a break in the graph, but we have points on both sides and it's higher than both of them, so it counts as a max. Local min, so lower than surrounding points. So this doesn't count because it's an endpoint. I don't have points on both sides. The one that you guys miss a lot is this point right here. That is a local min because the points on either side of it are on the curve and they are above it, aren't they? So our first local min is at 1, 3. We have another local min at 2, 2. And another one at 5, 3. Right there. It can either way, as long as it's lower than the points on either side. Okay. Next page. Okay, these were some of my favorite questions on this study, guys. You really have to think about some of these. So, 12 through 16. What do we want to talk about? 14, 16, 13, 12, 15. How about everything? So let's do this page. Okay, problem number 12. Absolute, max, and min. So we did one a little bit earlier that was a polynomial. This one is a little bit uglier. If we want maxes or mins, we have to do the derivative. So the 1/3 comes down, inside stays the same, subtract 1 from the power, times, what's the derivative of the inside? 4. Okay, it might help you to rewrite this like a 4/3. A negative would be on the bottom. That's like a cube root of 4x plus 8 squared. Critical points are where this derivative is 0 or undefined. If you set this thing equal to 0, you would multiply the bottom over and you get 4 equals 0. Does that happen? No. If it's undefined, the denominator is 0. What would make that denominator equal 0? -2. So my only critical point is at -2. That is in my interval. So for my absolute, max, and min, I have to test all 3, both endpoints and my critical point. So this is like a cube root. If I put in a -5, I have a -20 plus 8, so -12. Obviously on this test, I'll give you, somewhat nice numbers. But let's just leave this like that for a second. -2, if I put that in, I get the cube root of 0, which is 0. If I put in a 0, I get the cube root of 8. Okay, I don't even really need these decimals, because what kind of number is this one going to be? A negative. That's my only negative, so it has to be my absolute minimum. I have a 0, and then this would be a positive, so it's the absolute max. Number 13. This was, I had an example like this in our notes, and when we did this quiz, this was your bonus question. It was something like this one. Does there exist a polynomial function such that f of 0 equals -1, f of 2 equals 4, and the derivative is less than or equal to 2 all the time? Okay. If I look at this, it tells me it's a polynomial, and that is a really important piece of information. Because if it's a polynomial, that means it is continuous and differentiable, right? So, the mean value theorem has to work here. Mean value theorem tells us that somewhere the derivative is equal to the slope between the endpoints. So my endpoints were 0, -1, and 2, 4. If I did this slope, y2 minus y1 over x2 minus x1, I have 5 over 2, or 2.5. So the mean value theorem tells me that somewhere my derivative has to equal 2.5. So is it possible for the derivative to always be less than 2? No. So it has to equal 2.5, so it's not possible to always be smaller than 2. Questions on that? Number 14. Okay, I want to show that f of -1 equals f of 1. So if you put in a -1, this is like saying the cube root of that number squared. So that's like 1 minus the cube root of 1, and you get 0. If you put in a 1, you get 1 minus 1, so we get 0. So those are the same. But there is not a number in the interval where the derivative is 0. So if we find this derivative of 1 is 0, minus 2/3 x to the negative 1/3. That's negative 2 over 3 cube root of x. If you set that equal to 0, you get negative 2 equals 0, which doesn't work. So I want to know, why doesn't this contradict Rolle's theorem? Rolle's theorem tells us that if the endpoints are equal, which these were, somewhere the derivative is 0. So why didn't that work? Wait. Yeah. Remember, Rolle's theorem has conditions. It has to be continuous and differentiable. Continuous, you can put any number you want into a cube root, right? Differentiable, when I find this derivative, it is undefined at x equals 0, which means my function is not differentiable at 0. 0 is in the interval we're looking at, so it's not differentiable. That means we can't use Rolle's theorem. So your explanation would be Rolle's theorem doesn't apply since the function isn't differentiable on the entire interval. So questions 13 and 14 were really mean value and Rolle's theorem questions, but I was just trying to get you to think about them a little bit differently. Think about what they mean and when they work. Are you ready to go on to the next one? I think I'm going to draw this picture up here so I can. Okay, so I gave you a graph. Okay, and it looks like this, roughly. told you, this is the graph of f prime. This is not the original, this is the derivative. So part A, I want to know when the function is increasing or decreasing. Now we normally find that by finding the first derivative and making the sine line. Okay, this is really just like your sine line. My critical points are where this thing was 0, which was 1, 3, and 5. It's positive before that, so that's plus, negative, positive, negative. Okay, and then normally we look at that number line, and anywhere it's positive, we would say it's increasing. So this graph is increasing where this first derivative is positive, which is from 0 to 1 and 3 to 5. It is decreasing where your first derivative is negative, so where it was below the x-axis. So we're looking at your interval here. That's from 1 to 3 and 5. Let's see, this graph stopped at 6. It didn't keep going. Oops. Okay, do you guys all see how I got the increasing, decreasing? Second question is the maximum or minimum. So I recommend, if you're struggling, draw the number line because you're used to telling the maximum or minimum from that. We could look at this and say, okay, this was positive, so increasing, then negative, so decreasing. Or if you have this number line, it's really easy just to sketch in, increasing, decreasing. So what is 1? Max. At 3, it was decreasing and then increasing, so that is a min. At 5, increasing to decreasing, so that one was a maximum. So if I give you the graph of the first derivative, just turn it into that sine line, and then it looks how you're used to answering those questions. Is everybody comfortable on how I went from the graph to the sine line? Problem 16. So I gave you one graph, but I'm going to have you look at it several different ways. So on part A, suppose this is just your function, your original function. I want to know the inflection points. So the inflection points are where your graph switches concavity. Okay, it's kind of sometimes hard to tell. If we look, this is definitely concave down. And we can tell right here, this is concave up, right? So it has to switch from concave down to concave up in the middle, so that would be approximately right here. So that's when x is 3. Okay, this is concave up, and here it's obviously concave down. So we're going to switch in the middle, which is about right there, so that one is at 5. I did ask you to give reasons, so your reason is just the concavity changes. And we can see that on the graph itself. Second, now let's pretend this is the first derivative. Okay, inflection points happen when the second derivative is 0. If this is the first, I will have an inflection point when the derivative of this thing is 0. When would this derivative be 0? When you have maximums and minimums, right? So that would be here, here, and here. Those are where you have horizontal tangent lines, so that's where the derivative of this thing would be 0. So that is where we would have our inflection points. So that's at x equals 2, 4, and 6. And our recent horizontal tangent lines. Okay, part C. If this is the second derivative itself, then the inflection point is when this second derivative is 0, which is here, here, and here. So that would be at 1, 4, and 7. The reason is because that second derivative is 0. Any questions on that? So we can go back to question 1. There were 3 of those that you had to do everything for. I could probably do one of them. Do you guys have a preference, A, B, or C?
C.
C? So the first thing I asked was the domain. We know that in a fraction, the denominator can't be 0. So x squared can't be a positive 4, which means x can't be plus or minus 2. Write that as negative infinity to negative 2, union negative 2 to 2, union 2 to infinity if you did the interval. Then I asked for x and y-intercepts. The x-intercept is when this whole thing equals 0, which in a fraction is really just when which part of it is 0? The top. So the top equals 0 when it's 0. Y-intercept, if you plug in 0 for all of your x's, you get 0 over negative 4, which is 0. So x and y-intercepts were both 0. I told you to skip C. So D was the asymptotes. So vertical asymptotes are really closely linked to your domain. Whatever x can't be in your domain, those are your vertical asymptotes. So we have them at negative 2 and positive 2. For the horizontal, how do you work that out? Okay, I can't just plug infinity in here because I get infinity over infinity. But, remember we divided by the highest power of x. So if you take top and bottom times 1 over x squared, you get 1 over x minus 1 minus 4 over x squared. Then a number over infinity goes to 0, so this is 0 over 1 minus 0, which is 0. Horizontal y equals 0. You will have to show that work for how you're getting that asymptote. Okay, E. I asked for increasing, decreasing, so we need the derivative. It's a fraction, so we have to do quotient rule. Low, d high, minus high, d low, over low, squared. so there's my derivative. We need the critical points. That's where this thing is 0 or undefined. If you set the top to 0, get x squared equals -4, what kind of numbers is that giving me? Imaginary, so I don't need those. And we've already found the bottom is 0 at plus and minus 2. So those are my only critical points. So, that's fun. For increasing, decreasing, we need our sign line. So we take our test points. Where do we plug these things in? Right here. So if I put in -3, that's 9. So -9 minus 4, that's negative over positive, so that's negative. Put in 0, we get a negative over a positive, which is negative. Put in a 3, we're also getting a negative. So this thing is negative always. Does that mean I can just say it's decreasing from -infinity to infinity? No, because we have asymptotes. So we have to say decreasing -infinity to -2, union -2 to 2, union 2 to infinity. F, I asked for maximums or minimums. If this thing's always decreasing, did we get any maximums, minimums? No. Right. G. I want the inflection points and concavity, so we have to do second derivative. So low, d high, derivative of the top, -2x, minus high, d low. So the 2 comes down, inside stays the same, subtract 1 from the power, times derivative of the inside, over low squared. So now it's to the 4th. Now you want to make your life as easy as possible, and you see we have this x squared minus 4 everywhere, so we could cancel one of those out. So this would now be to the 3rd. Okay, so I can distribute -2x cubed plus 8x. Okay, 2 times 2x is 4x, so I'm going to distribute a -4x. Okay. So then we get a 2x cubed plus 24x over x squared minus 4 cubed for the derivative. Inflection points are when this is 0 or undefined. I know it's undefined at positive and -2. If you set the top equal to 0, you could take out a 2x. If 2x equals 0, that happens at 0. X squared plus 12 equal to 0, what kind of number would that give me? Imaginary, so I don't need to worry about that one. When we go to graph our inflection points, we will need ordered pairs. Can you plug plus or minus 2 back in the original? No, because those are the asymptotes. If I put in the 0, we get 0 over -4, so that's 0. So just know when I go to graph this, the only actual order pair I'll have is the 0, 0. Now we need our concavity, so we need our sign line. We're putting them into the second derivative. So if we put in a -3, put in a -1, put in a 1, and put in a 3. Thank you. So this is concave up where it's positive from -2 to 0 and 2 to infinity. Concave down where it's negative. Negative infinity to -2, union 0 to 2. And the last thing I asked you to do then was draw your graph. So we plot everything we found. We know that we have intercepts, x and y-intercept are both at 0. We had vertical asymptotes at positive and -2. And a horizontal asymptote at 0. We had no maximum or minimum to mark. Our only inflection point was at 0, 0, so I'm just going to put an X there as well so I know it's an inflection point. My graph is always decreasing, so it's always falling. From -infinity to -2 is concave down. So falling and concave down, it would have to be down here. Make sure you're drawing your curve getting closer to your asymptotes. In the middle, we're still falling. We are concave up until we get to 0. Concave down from 0 to 2. And still falling over here, concave up. That should look like that. We have about 5 minutes. Are there any other questions? So if you do have questions, come in, talk to me about it. If you need to check the couple that we didn't go over, the answer key of course is in here. Test is tomorrow.
Thank you. Anybody wants a cupcake right in front of your room? Yeah, I've got too many slides. Matthew, do you guys want a cupcake? Go get one. There, you gotta like ice one.
I probably didn't get one, but I sure can if you want to come by later today. Okay, thank you.
So you're never running. I didn't know that.
Yeah. I'm going to print them. So if you want to come by, okay.
And just work on it.
I'll print them. Does anybody else want a blank study guide?
I do.
Okay. I'm going to print them now and run down and grab them in between classes, so I'll have it in here after that. You can wait or come back at some point today.
Plus, like, something like two, but there's so many. Right after I scored.
That was John. Oh, he is what John did. Yeah, look, John.
Our horticulture test is Friday, right?
It's not class you went. I'm playing that. Huh? Oh shoot. What's that over again?
The chart.
Wait, oh. What's wrong?
We're gonna
Cameron, would you go and ask Miss Lee for tissues? I've been out for 2 days and I keep forgetting to. Thank you. Okay. So we have several things to do today. You have homework to turn in to me. We have the little quiz we're going to do, and I'm going to finish the section 3.2 notes. So I think I'm going to finish the notes first, and that way, when you finish with your quiz, you can start on your homework and not just sit and be waiting for me to get to that. And the homework, we will grade it if we have time in class, otherwise I'll just collect it at the end of class and look over it myself. So get out that notes handout I printed for you yesterday. How is everybody today?
I had to wake up, so we're off to a bad start.
Oh, now that's not so bad. Where is Sierra? You guys know?
She was.
Thank you, just set them up there.